everybody, welcome back to the channel. Today I want to do a very quick crash course on significant figures. Now, if you've had me before, you know I'm a stickler for those significant figures, and that's because in my undergraduate degree, when I was taking all my chemistry classes, and in my master's program, when I got my master's degree in chemistry, we always had to work with significant figures, which is why I have you guys work with significant figures. They are pretty important in chemistry calculations. Before we get into the significant figure rules, I just want to talk about why significant figures are important for a second. So in science and in chemistry in particular, we do a lot of measuring. So you are measuring the amount of liquid in pipettes, graduated cylinders, you're finding the mass of different things, you're getting you're reading things off of instruments, like you might be reading the absorbance for something, for a solution in a spectrometer. And each of those numbers is not exact. And what I mean by that is, let's say you are massing 1 gram of salt on the scale, and that scale reads 1.00 grams. That mass is not exactly 1.00 grams with infinite zeros coming after that one. That scale only reads those 2 digits after that number 1. Therefore, that 1.00 only has a certain amount of accuracy to it. So therefore, that particular number has 3 significant figures, because we don't know what those additional numbers would be after that 1.00, because the scale doesn't read that far. I've grabbed this from my cabinet just to show you, but I have this water bottle. Of course, it might be backwards for you, I'm not sure. And this reads to us in units of milliliters up here. So of course it goes all the way down, right? So from 100 all the way to 1,000 milliliters. If you were to if you were to find the volume of, let's say, 300 milliliters of liquid in this particular measuring device, this measuring device is not that exact. This is an approximation. If you fill this up to this line, this is approximately 300 milliliters. This water bottle does not need to be that exact because it's a water bottle. We're not doing chemistry calculations with this. So each of these measurements right here, if you were to fill this up, would have only 1 significant figure. It's approximately that much. If you fill it up to this line, that's not exactly 400.00000 infinite milliliters, because this isn't meant to be that exact. It's approximate. And that's where significant figures comes into play, when it's how exact are our measuring devices. Are they not meant to be that exact, or are they meant to be super exact, like what you would find in some chemistry labs? And of course, chemists don't just sit around all day and count the number of significant figures in numbers, but they need to do calculations with them, because your answer in a calculation can't be more precise than the measuring equipment that you're using. So that's what we're going to go over in this crash course. And I'm also going to show you a little bit about scientific notation, just how to convert into scientific notation and out of scientific notation back into standard form, because on your AP exam, you will have to do quite a bit of that. So let's get out of this introduction. That was a long-winded intro, I'm sorry, and let's get started. So like I said, with significant figures, we're not just counting the number of sig figs in any number. You're not going to use these in your math class, because your math class numbers, when you're given problems, they're typically not going to be measurements, they're just numbers. However, in chemistry or in your science classes, we're dealing with measurements. So I just wanted to make that clear, that the reason why we do this with numbers in chemistry is because there's a certain amount of uncertainty in our measurements, not just numbers. So anyway, these are the chemistry 1 and 2 notes. This is what I normally give my students, so I'm just going to run through this really quick. So rule number 1 says that all non-zero numbers are significant. So if you have a measurement that has any number between 1 and 9, those numbers are always considered significant. So for example, if I have the number 87, let's say the distance from here to, I don't know, the distance from here to Newark, it's not that far, but whatever. is 87 miles. It's an approximation. It's about that much. It's not that exact. That number has two significant figures. Both of those are pretty certain. We could say it's about 87 miles away, but we don't know those other digits after that. So that would have two significant figures. Any number that's not a zero. Once you start introducing the zeros, that's when you kind of have to be careful with your significant figures. One rule that deals with zeros has to do with when zeros are in between numbers that are not zeros. So I always say that that's a trapped zero or a sandwich zero. So if you have a zero that's surrounded by numbers that are not zero, or from 1 to 9, for example, the number 209, the volume of the solution was 209 milliliters. That zero that's sandwiched or surrounded by non-zero numbers is considered significant in this case. That number is important. It's a part of that measurement. It counts. So that has three significant figures. Here's the one where some students always get a little tripped up by, but when a decimal is in the number, the first non-zero number present and all the numbers after it are significant. So if I have the number, let's say 9.70, the mass of the product was 9.70 grams. You put that on a scale and that's what you found. That zero is considered significant. That's what the scale is reading you. That zero counts. It's important in that measurement. 9.70 therefore has three significant figures. If I had 9.700, both of those zeros would count. And the more expensive the scales get, the more decimal places they read. But scales are like a fortune. So for you to read a lot of digits after the decimal point, it would be a heck of a lot of money. As opposed to this number where there's zeros in the front of the first non-zero number. So here you'll see I have a zero in the front and I have two zeros before the first non-zero number as well. What I always tell my students is put your pencil down and you're going to cross out all the zeros in the front of this value or in this measurement. And your first non-zero number that's present, which happens to be the 4 here, and everything after it is considered significant. So this particular measurement would have one significant figure. I didn't always understand this rule, but I do know why it is that way. So because to me, it's like, okay, well, if I have 0.004 milliliters of something, why wouldn't those zeros count? Well, technically, those zeros in the front count as placeholders. That's the scientific way to describe it. They're placeholders because technically, this number could be written in scientific notation. And when we rewrite it in scientific notation, your number of significant figures changes actually because those zeros technically do count as placeholders, which kind of segues us nicely into the fourth rule. So when a number is written in scientific notation, all of the numbers to the left of the multiplication sign are considered significant. So if I had the number 6.023 times 10 to the 23rd, hopefully you recognize that is Avogadro's number. That number or that measurement has 1, 2, 3, 4 digits to the left of the multiplication sign, and therefore all 4 of those would be considered significant. And those are all the rules you need to know to just count the number of significant figures in measurements. But like I said, chemists don't just sit around and count the number of sig figs in numbers. They need to do calculations with them. So let's go over the rules for how to calculate with significant figures using addition, subtraction, multiplication, and division.
Something else I wanted to add to those rules are that those rules and counting significant figures are only good for measurements. So some numbers that you might encounter are not measurements, they're exact numbers. For example, the fact that there are 1,000 grams in 1 kilogram. A lot of times students will look at that in a dimensional analysis problem and they'll say, well, those numbers have one significant figure, so I rounded my answer so it had one. No, that equity, that conversion factor, the fact that there are 1,000 grams in 1 kilogram is exact. There's exactly 1,000 grams in 1 kilogram. So those numbers in that case would have an infinite number of significant figures. If you were counting the number of students in the room, there are 10 students taking AP chemistry. You can count 10 students, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's a counting number, that's not a measurement. So in that case, the fact that there are 10 students, that also has an infinite number of significant figures. There's no uncertainty in that because I don't have fingers and toes in drawers around the room. There's exactly 10 students in the class. Another one, I'll give you one more. 24 hours in one day. There's exactly 24 hours in one day. That also has an infinite number of significant figures. There is no uncertainty in that. I just wanted to throw that in there as well after going over how to count the number of significant figures in measurements, because when you're not dealing with measurements and they are exact counting numbers, each of those values would have an infinite number of significant figures. Let's get to the calculations.
So there's two rules, and one rule corresponds to addition and subtraction, and the other rule corresponds to multiplication and division. Both rules are really easy. You just have to know what both of those rules are. So for addition and subtraction, your answer has to have the same number of digits after the decimal point as your number that you're adding or subtracting that has the least number of digits after the decimal point. The less digits a measurement has after the decimal point, that means all of those digits are not certain. And if we're not certain about those digits that aren't there, then we can't be too certain about our answer. I can't have a super exact answer from the addition of two measurements that themselves aren't that exact. So, or aren't that certain, I should say. So we have to take that into consideration. I just have three measurements here, a very, very basic problem. So 7.939 plus 6.26 plus 11.1. You add all of these up and your calculator tells you the answer is 25.299. And this answer is pretty darn precise. However, this number here, this 11.1, only has one digit after the decimal point. We don't know what those digits are after that. So therefore, we're not 100% sure about these numbers after that. This could be 11.11, which makes this answer different from what the calculator is telling us right now. So because of that, we have to round this answer to reflect that. And we want to round it so it only has one digit after the decimal point, because that's how certain this number is. And I can't be more certain than my least certain measurement. Therefore, your answer, you would round that up to 25.3. And that's the rule for addition and subtraction. And you would do this in any problem that requires that. Multiplication and division, on the other hand, is a little bit of a different rule. So you don't have to worry about the number of decimal places that come after the decimal point. Instead, you just have to look at how many significant figures each individual number has. So your answer will have the same number of significant figures as the number with the fewest sig figs that was used in that calculation. I always think it's a little bit easier to actually do a problem than it is to talk about how to do a problem, because that's a very, very wordy explanation. So if I have this, let's say I'm trying to find the area of a cube, or the volume of a cube. 27.2 times 15.63 times 1.846. Each of those numbers has a different number of significant figures. So this first one has 3 significant figures based on the rule. And these guys have 4 significant figures based on rule number 1. So when you type this in the calculator, your answer is going to give you this ridiculous number, 784.801,056. I mean, this cannot be the answer, because look how exact this number is. My measurements aren't even that exact. So therefore, my answer can't be more exact than my least exact measurement. So therefore, we want to round this number so it has the same number of sig figs as the number used in the calculation with the least. So this number has 3. which happens to be the lowest. So that's how many significant figures we want to round this answer to. Therefore, how do we round that? What's the answer? The answer should be 785. And you would do the same thing for division problems. When you're doing calculations with multiple steps in them, so you might have a division and then you might have to do an addition after that, you always want to take it one step at a time. So in that worksheet that you have, you're going to see you'll have to do like a multiplication first, and then you have to do an addition depending on parentheses. Keep the significant figure rules as you're going. So I wrote mine out to represent that. So if there was a number in parentheses, I did that first, and I found my answer to the correct number of significant figures based on that operation. Then I did the next operation and kept the number of significant figures based off of that one. So you have to go back and forth with the rules in those problems for whatever that third section, I think it is, on the worksheet. So make sure you follow those every single time and look at my answer key. Look and see how I did it, what step I did first. Remember PEPMDAS, right? Powers, parentheses, multiplication, division, subtraction, addition, or addition, subtraction. Remember that, and that's the order in which you're supposed to solve the problems. If you have any questions on those, let me know.
So numbers are written in scientific notation when you have a number that's either equal to or greater than 1, but also less than 10. And the way you represent that is multiplying it to some power of 10. And that power of 10 can be positive or it could be negative. And basically it's saying how many times are you multiplying that particular number by 10 when you move the decimal point over. So for this first one, you always want to represent scientific notation with one number and then a decimal point. Again, because it has to be between 1 and less than 10, but it has to be one digit and then a decimal point. So if I have this number 285.67, my decimal point is in this position right here. You want to move this over until I get in between this first number and then those numbers after that. Now this particular number has 1, 2, 3, 4, 5 significant figures. So when I put this in scientific notation, your answer should still have 5 significant figures. So I'm going to take that and put 2.8567. And again, we're saying how many times are we multiplying this number, 2.8567, times 10 in order to get 285? Well, you move the decimal point over 1, 2 times. So essentially, you're taking 2.8567 times 10, which gives you 28, times another 10, which gives you 285. You're timesing it by 10 twice. And that's what we use with those exponents, the 10 to the second power. In this case, I have a number that's less than 1. So again, we want to move that decimal point so you have one digit and then the decimal point and then however many digits come after that. So in this case, 1, 2, 3. I have to move that decimal point over 3 times. But notice this number is less than 1. So let's just write the number down first. 3.5 times 10. We're timesing it times 10. However, you're moving in the opposite direction here. You're moving to the right. So because you're moving it to the right 3 times, it has to be -3. Basically, what that's saying there, if you have a negative exponent, you're dividing it by 10 3 times. So it's 3.5 divided by 10, which gives us 0.35, etc., until you get to 0.0035. That's the whole idea behind what scientific notation is how many times are you multiplying by 10, and it's multiplying if it's a positive exponent, or how many times are you dividing by 10 if it's a negative exponent. But you also have to keep your significant figures through this. You want to keep those rules. This number here actually only has one significant figure. Let's do 2 sig figs there,
5 sig figs there just to stay consistent. So therefore, your number written in scientific notation should also only have one significant figure. Here's my imaginary decimal point. You don't want to add the decimal point to that because then it changes the number of sig figs in your answer. You don't want to make a measurement more certain than it really is. So to get this, you want to move that decimal point over 2 times. So we still want that one significant figure, so it's 5. Well, we would just say times 10 to the second. This one, on the other hand, obviously it's the same exact number, but the certainty of the measurement's a little bit more exact here. So we do want to follow through and have 3 significant figures in our number written in scientific notation. So my answer here would be also times 10 to the second. This number here, so we have a number that's less than 1. Let's move that decimal point over. Looks like we move it 1, 2, 3, 4 times. Now I literally still do that as, 33 years old or whatever and took all this education. I still do 1, 2, 3, 4. 2.0 because we have 2 significant figures. And we're going to times 10. 1, 2, 3, 4. But it's less than 1. So we have to divide it by 10. We have to divide it by 10 4 times. So therefore, that would be my answer. Now this number is already written in proper scientific notation. However, I just wanted to show you something. So if you have a number like this, technically you can write that in scientific notation. How many times do you have to multiply this by 10 to get this number here? No times. It's the same number. So that's also okay. You might also see times 10 to the 0th power. You're timesing 1.26 by 10 0 times to get this number right here. I just thought that was a good example to show. This one, I have a number bigger than 1. So 1, 2, 3, 4, 5, 6, 7. My decimal point's going to go right there. 7.8 times 10, very large number, greater than 10, so we have to times it by 10 7 times in order to get that. Keep all your significant figures here. This is a pain in the neck, but keep your sig figs. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I move that over 10 times. 8.874793 times 10 to the 10th. However, we have to divide it by 10, so we're going to do a negative exponent there. That's how you take a number in standard notation and you write it in scientific notation. Basically, we're doing the opposite here. So rather than putting it into scientific notation, we are putting it into standard notation from scientific notation. So just like before, so we're taking 5.4 and basically we're timesing it by 10 3 times. So because you're timesing it by 10, all you have to do is move the decimal point over 3 times. So 5, 4, if my decimal point's here, I would move it over 1, 2, 3 times. So you would have to tack on 2 additional zeros. Don't put a decimal point at the end because this number has 2 significant figures and therefore this answer should also have 2 significant figures. So you're moving like the imaginary decimal point over. This number, so notice it's a negative exponent, so we have to divide this answer, or we have to divide this number by 10 6 times. So we're going to move the decimal point in the opposite direction to the left. We're going to move that over 6 times. So I'm starting off right here. We'll have it 1, 2, 3, 4, 5, 6. My decimal point would go right there, and you would just add all your necessary zeros in. So your final answer, 1, 2, 3, 4, 5, 8, 0, 1, 3. 2 more. These numbers might look familiar to you. These are both used in Chem 1. So 3 times 10 to the 8th is the speed of light. So, or the speed that all electromagnetic radiation travels at, really. Here's my decimal point. Move that over 8 times. So I have 1 starting right there.
6, 7, 8. Essentially, you're going to add 6 zeros after that. The way you can make zeros significant in a number like this, the way I always taught, was you could put lines above them. And so that will make those first 2 zeros significant. And you can add commas if you want. Essentially 300 million. Now this is why we write numbers in scientific notation, is because to write this out all the time would be a pain in the neck. So this should look familiar to you. This is Planck's constant, which we also use in this unit when you're trying to find the energy of wavelength given the frequency. You might remember the equation E equals h times nu. That's h. So we would move this over 34 times because it's less than that. We're dividing 6.626 by 10 34 times. So basically you would have to write 33 zeros in front of that because you moved it over 1 time. You still have 33 left. 33 zeros. So let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33. Whew. Basically, that's what it would look like. All of those zeros with the 6626 at the very end. This is why it's important to write numbers in scientific notation. I just wanted to go over this with you because you do have to be comfortable with converting numbers in and out of scientific notation very easily. So I just wanted to give you a little bit of practice with that. Of course, if you have any questions on scientific notation or on significant figures, email me, let me know.